Hi folks, just starting up in a minute, getting myself organized. Good morning, folks. Great to have you here on a cold Thursday morning. I'll start my recording now. Good morning, everyone. Welcome to part 2 of our memory week here in COMP2300/6300, semester 1, 2022, on a cold Canberra morning. I think it's the first cold morning down here as we're heading into autumn now, early March. Folks, we've had a big week looking at how memory works on the Microbit. You've been working in your labs on starting to understand how to move around in a program using branching and labels. And we've been doing some little experiments. Some folks have asked some very interesting questions on the piazza that have really got me thinking, and I've learned a few things since I'm doing a bit of an investigation about those. So thank you for doing that, and I hope you keep asking great questions. Just going to check my dashboard to see that everyone's watching. Oh, I've got a few early birds. It's about 15 folks on the streams. Wonder if there's anyone watching on. There's a couple of viewers live on Microsoft Stream as well. Thank you so much, folks, for joining us today. Well, today we're going to continue talking about memory. We're going to go a little bit deeper into branches and start to look at the condition codes in assembly. We are not going to be able to cover everything to do with condition codes because we have a whole week, next week, to talk about control structures, structured programming. You already did structured programming. You did Comp 1110 last semester, but we get to look at it in a different way, in the assembly programming way, which, as you know, the way I put it is that this is the way that your computer actually does things, not just the way we write about how it does things. Now, I'm just going to get myself on the team in case anyone has an amazing question. So far, think about your questions. I'm going to talk for a few minutes about something very important, something very useful to students. So if they're not here now, I'm sure that the other students will watch this video this afternoon, because I'm going to talk about assessments that you have over the next week. And this, we're at week 3, you know, things have gotten started. We're 25% of the way through the course, actually, once you complete week 3. But at the end of week 3, we start to have a few more assessment items that are either due or available. Things start to get a bit real in your courses by this week. So I want to draw your attention to the assessments page on the website, on the COMP2300 website, right here, assessments. We've got our assessment scheme table, and I just made this table like the most important thing on this page, because I think it's the way I want you to think about the assessments, is going through time. You've been working on lab tasks in labs, and I've just clarified the lab tasks page and clarified as well that the date that your first lab pack is due is Tuesday next week at 8 a.m. The reason it's due at a weird time is that I want to give you as much time as possible to revise those labs. Ideally, you go through and attempt every task, get a decent little program in the task file for each task, and you get full marks for the labs. The labs are not supposed to be hard. Everybody who's attending regularly and doing their work should be getting those marks. I've given you the whole of the weekend, all the way up until week 4's first lab, because I want you to have maximum time, but I don't want the lab packs to be delayed until like the following week's labs, right? People should be only focusing on one lab pack at a time. So you get up until the start of that week. I've put the due dates in for the other lab packs as well, so you can put those in your calendar if you want to be very organized. But basically they're due at the end of each block of 3 weeks in the course, or the weekend, just the start of the next week after that. Lab tasks, that one you're doing, that one is fine. One thing that you won't have been doing and you can't actually do yet is the first quiz in COMP2300. So we have 2 quizzes which will be available on Wattle. 2 quizzes on Wattle. And well, someone started a meeting in general, which is exciting. Good on them. 2 quizzes available in Wattle. These quizzes are worth 1 mark each. They're very low number of marks. They're basically like doing a practice exam, because they're questions which are often taken from our mid-semester and final exams in COMP2300 and turned into a learning experience for you. The good thing about the quiz is that you get to do it as many times as you like. It automatically marks it, gives you the feedback right away. And if you want to do better, just learn the material that you feel that you're weaker on, or talk to a tutor about it, or ask a good question on Piazza in a general way, not about the specific questions, and attempt the quiz again. So you get as many times over the whole of next week to do quiz 1. And I would highly encourage everybody in this class to take advantage of this opportunity to test your learning in a quiz and try to understand some of the concepts we've been going so far. You will get a pretty you may get a shock, I suppose, because it's one thing to understand something in the lecture as a general concept. We're having a conversation, you think, oh yeah, I can understand that concept. It's quite a concept to be asked a question. For example, if someone gives you a binary number and says, okay, take this number and how is it going to be represented in memory following a store operation on the Microbit? And just out of your head, you've got to do the little endian switch, remembering the way to do it correctly in hex. So sometimes that can be a bit challenging. I'm not saying that it's hard. Each of the individual questions in the quiz is not hard, but it's certainly a challenge to do them all at the same time. There are 10 questions. I would expect everyone to need about 90 minutes to complete the quiz. If you do it in less than 90 minutes, great. If it takes you a lot more than 90 minutes, that's a bit of a worry, because that amount of time is about the way that I calibrate the amount of time for the exams. So the mid-semester exam, which is not a quiz, will also have 90 minutes. You'll also have 10 questions. So if you find it very difficult to do the quiz next week in 90 minutes, you might need to practice it a few times so that you can get to that level of familiarity with the material. The quiz gives you feedback every time you complete a question. You'll click a button that says check, and it will tell you which options were right and which options were wrong. And it will give you some feedback about why that's the case automatically. So you won't necessarily need to ask anybody about your answers. In fact, I would advise that you shouldn't ask anybody directly about the quiz questions next week. For the whole week, we'll have like a blanket ban on specific quiz-related questions on Piazza. But if you want to ask about like how we store numbers in memory, right? That's a general concept. Of course, we're going to answer that on Piazza. And I would encourage you to talk to your colleagues about the parts of the course that you don't quite understand yet. So that's the quiz. You get the whole of week 4 and a little bit extra on each side. And I really hope you take advantage of it. It should be really interesting. Going down the row, the next thing which is important is assignment 1. Assignment 1 is due on the last day of week 6, just before the mid-semester break. And assignment 1 has now been released. And you can now go and see what assignment 1 is about. The name of assignment 1 is Light Show. And your goal in this assignment, your task, is to create a little light show on your Microbit using the LEDs. You might be thinking, I don't know how to use the LEDs on my Microbit. This is going to be a difficult assignment. I can assure you that by the end of week 4, you will know how to use the LEDs in your Microbit, because week 4's lab is all about using the LEDs. I'm going to go through the assignment in more detail later as we get towards the related activities. But I just want to say today, you can go and look at the assignment and start thinking about what this challenge might mean, what you might like to do, and try to understand what the assessment task is asking you, because it might be an unfamiliar type style of assessment, really. There's a pretty clear specification about what you have to do. The really technical version is you must use the LEDs to create a light show that changes over time, and it must be engaging for at least 30 seconds. It must never stop, and it must work when the Microbit is powered over USB but not connected to a computer. Really, that one is just to say it's a light show which you're not supposed to be using the debugger to go through different steps. You have to press start and have it continue without you pressing down in the debugger or something. You should be using memory to get this to work. Using memory is something which I have been hammering you folks about, saying get used to it now, because it's really important for making complex programs. I know there's some people in the class who will want to learn to do everything all at once. I don't want you to do that. I want you to focus on program flow, LEDs, and outputs in this assignment. So you're not allowed to use the buttons. You're not allowed to use any input peripheral on the Microbit. It's only outputs with the LEDs. And if you want to, you can use the speaker, but we're not going to talk about that today. So just to clear, narrow the scope a little bit about what's expected here. You must, in this assignment, and this will be the case for the second assignment, write a design document. The design document is a very important part of this assignment. It's not a long document. The maximum is 600 words. It's going to be a markdown file, and it's supposed to explain what your design does, what your program does, how you did it, how your program works, and why your design choices are the appropriate ones for that task. So what, how, and why. We've found in previous years that the design document concept can be a bit challenging for some students. Particularly, I know that there's students who have done other types of writing tasks before, reports or statements or answers or solutions or essays. I guess we've got this concept in 2300 of having a document which is answering specific questions about your design. So I would advise you not to make assumptions about what we want to see in that document, and in fact to look at the actual question, the specification, and then also look at this long page in our resources about how to write a design document. So you can get stuck into that and start to understand more about design documents. So in this assignment, you're going to make a program in ARM v7 assembly. You're going to write a design document. In fact, the marking criteria are split evenly between those two outputs. So the marking criteria are these: the sophistication of your design and how it meets the assignment specification, that's 20%. The sophistication of your implementation in ARM v7 assembly, 50%. Sophistication of analysis and evaluation of why your implementation is correct and appropriate and what limitations it might have, 20%. Sophistication of communication and expression, 10%. Now, item 2 will primarily, that's the sophistication of your implementation, that will be primarily evaluated through your program code. And items 1, 3, and 4, the explanation of your design, the analysis and evaluation of why it's correct and what limitations it might have, and the communication and expression, those items will primarily be evaluated through your design document. Of course, we'll look at both things together, but when we're making a decision about the mark, we need for both of those things to be there. So you can't just hand in the code and not do the design document and expect to pass, basically. Similarly, you can't just hand in the design document and no code and expect to pass. You need both of the items. They're both equally important to be there. If you look at the getting started part of the assignment, it says, first thing, read the page completely. That's a good idea. Fork and clone the assignment template, which is now available on GitLab. Good idea. Number 3, complete the pre-submission task. Well, hang on, what's the pre-submission task? Actually, before you even start your assignment, I want you to start writing a different document called the design proposal.md, which is in your assignment template. You can look at another assessment item. The assignment 1 pre-submission has its own page that explains how you're going to begin planning your assignment. And the idea of pre-submission is that pre-submission prevents pretty poor performance. The 5 Ps. The idea here is to have an idea about what your assignment is going to be, write it down, articulate that idea. That's hard work. You don't have to write that much, less than 200 words. You show that to your tutor, and then your tutor can have a real conversation with you about whether that's a good idea, what you might do to improve it, and how your approach might be helped by some knowledge that you don't have. This may be the most important feedback you get in the entire course. You get a chance to have a one-on-one conversation with your tutor. Your tutor will be able to see, read your assignment pre-submission idea, your design proposal for what you're going to do, and they can tell you, oh, that's amazing, but I think that this is going to be a little bit too hard. How about you start with this chunk to make it easier on yourself? Oh, great feedback. Alternatively, they might say, that's an interesting idea, but I worry that it's going to be too simple. I don't think that that's going to meet our standard for a good assignment, which would get a credit. A good assignment gets a credit. Very good gets a distinction. So that's very important feedback that usually you wouldn't get until you do the assignment and get the mark back. I don't want people to get their mark back and be disappointed because their idea was somehow not the idea we're looking for. That's why I've got this specific assessment task, pre-submission assessment task. It's worth 1% of your final grade, just to give you the chance to talk to your tutor about it and for your tutor to tell you what we're actually looking for if it's not what you're doing. So I really hope that everyone makes use of this opportunity. You don't have to do the pre-submission, but you won't get the mark for it if you don't do it. The process is as follows. You have to read the assignment specification. You should have already done that. You have to fork and clone the assignment template. You have to think about your idea for what you might like to do for your assignment. Probably do some reading around the website to get some context for it. Write it down in the design proposal file. You're supposed to explain the what and the how, very roughly, just in 200 words. Push your design proposal file before your lab in week 5. Before your lab in week 5. And in your lab in week 5, you will get to have that one-on-one conversation with your tutor. If you haven't pushed your design proposal file before your lab in week 5, when your tutor walks around, they will look at their computer and say, oh, I don't have a design proposal from you. There won't be time in the lab to write your design proposal in that moment. So of course, you can then have a conversation with your tutor, but you won't get a mark for the design proposal. So I think I've spent now about 20 minutes talking about assessment, but you can see that many of these links, which were previously not populated in the assessment scheme, are now active links. Quiz 1, lab tasks, assignment 1 pre-submission, assignment 1. That takes us up to the end of week 6. Our mid-semester exam, I think it definitely is scheduled for week 7, although it's only a draft schedule at the moment. So we won't have the mid-semester exam until you get back from the break, which is ideal, because I actually have to write the mid-semester exam. I have to do the work. It's not, I don't just have these things popping out of the sky. It takes time to write an exam. I don't want to do it by week 6, I'm busy. I'm busy teaching you lot. I need a break to write it. And then we worry about the second assignment after the break. So let me level with you folks. What is important to me in this course? What do I want you to do? I want you to do creative and expressive programs using the Microbit. So my goal with this assignment is that everybody in the class comes up with a unique light show, their own way to do it. Of course, you'll all use labels and branching and memory and et cetera, and ARM instructions, but you'll all go in your own direction. I want to see 400 unique and exciting light shows. We could have a light show exhibition, hang them all up. I'm also really, really focused on feedback to you about your learning. This is why I've got 2 assessment tasks before your assignment is due entirely dedicated to feedback. That's the first quiz. That's a feedback quiz. It's to tell you how you're going with your learning, give you a chance to improve in an important week, week 4, and just get that knowledge settled in your brain before you have to do any exams in this course, any hard exams. And then the pre-submission, where you have to think about your assignment, let that information settle, write down a design proposal. Writing something down is the best way to make sure that the idea is not just like this loose, ethereal concept in your brain, but it's something real. Have someone else read it who you trust, your tutor, and they can give you frank and fearless feedback about whether it's a good idea or not. And if the feedback from your pre-submission is it's not a good idea, that actually doesn't mean that your mark will be low in the pre-submission. It just means that your mark is based on how much or how sophisticated your attempt is to write a design proposal, right? If you've written a good proposal, cool, great, you get a good mark out of 1. If you write a very short proposal that doesn't really say anything, well, you're not going to get a good mark. But the actual idea is sort of a separate concept that's just being evaluated by your tutor in terms of how good it would be for assignment 1. That way we get the maximum number of people, hopefully everybody, doing assignment 1s, which are excellent and very good, and hopefully some satisfactory ones too. But what I want to see in this class as a goal, I'm really serious here, is I don't want to see any assignments that I would consider to be unsatisfactory. I find it really sad when students do work, they've tried really hard, we get it, and we're like, wait a minute, this is just not right. This is not what we were looking for. This is not answering the question. It's not meeting the specification. I'm sorry, that's not a pass. It's less than a pass. We don't want that for anybody. So we do all of this feedback. Okay, I wanted to have a long spiel about assessments this morning, and I think I've used up my time on it. Close tabs, close tabs, close tabs, close tabs. Back to memory. Now last time, just to refresh your memory, we talked about how to load memory. We talked about how to store into memory. You're loading from memory into a register, storing from a register into memory. And all of the load and store values involved using an address. That's the address, 0x2000000, and using this bracket notation, which indicates that you want Lido to treat R1 as an address and load the memory, the data in memory at that address. So we now have this concept with, when you're dealing with memory, that there's always two things. There's always the data that you want to get, and there's the address where it's located. The data and the address. Getting to our next slide. Okay, and we got to this topic. This was where we stopped. Memory address space. Flying through space, finding memory addresses. I'm going a bit crazy now, talking about Star Trek. No, we fly through space on our microbits, searching for particular addresses to load some data, much like the USS Enterprise in the famous show Star Trek would go to different planets, and the planets would always be recognized by a certain kind of designation, right? Rigel 7 or something, which would give you the location. I guess in that instance, Rigel would be the star. That one might be Rigel. And then around Rigel there might be a solar system with 7 planets or more, and so that might be the 7th planet in the Rigel star system. So you can see there is is a connection. There is a reason why I started talking about Star Trek just then. But you might find that similarly to the crew of the USS Enterprise, when trying to find things in different addresses in your microbit, there's a lot of empty space, and there's only a few little places where there is actually information available in your microbit. Similar to space, right? Space is mostly nothing, and then there's just these very, very long distances where in between stars, most stars don't have any planets, and some stars do. Most of those planets wouldn't be of any interest, but maybe occasionally there's one really interesting one like Rigel 7. So the address space is the set of all valid addresses. So if you've got on your microbit, your address space is every address which can be addressed by a 32-bit register. We have 32-bit registers. That means we get this many different addresses. There's 1,000, there's a million, 4 billion, 4.3 billion different bytes. Whoops, what have I got there? Somehow I grabbed whatever that thing is. Oh, it's my microbit. So you can address with 32 bits about 4 gigabytes of memory. Here's a question, is that a lot? I guess it's a lot for some things. If we only need to have a few bytes here and there, that's a lot of memory. But I guess for the big computer you have, your laptop or desktop, might well have more than 4 gigabytes of memory. My one has 32, so a 32-bit address is not actually going to be able to address all of that memory at once, and that's only the system memory, just the RAM for my system. There's, of course, a much bigger address space. So most big computers have what's called a 64-bit OS, or a 64-bit operating system, so that you can address more memory. There's some tricks they can use if you don't have 64 bits to address a bigger memory space. Like you have sort of memory space 1, memory space 2, memory space 3, memory space 4 or something, different spaces that you can switch in and out of. The Microbit doesn't do that. It's only got one memory space. It's got a 32-bit address. And we showed this diagram before, which was a picture of what the ARM v7m memory space looks like. Starting at 0, going all the way up to 4 gigabytes. And this diagram has, someone's asked me how I got 4 gigabytes. How did I get the 4 gigabyte value? Well, this is all of this space is, as I said before, is 4 gigabytes. The reason for that is that the lowest address is 0, and the highest address is all Fs. And what's that number in decimal? 2 to the power of 32 equals 4.3 billion bytes. Each memory address is 1 byte. So 4.3 billion bytes is about 4 gigabytes, about 4 GB, or exactly 4 gebibytes, I suppose, if you're going to be specific. Yep, very good. Someone's put the answer in there. Now, all of these sections are really important because they give us a place to start reading and writing. So you can see that the SRAM, when we wanted to read a bit of data, do a bit of normal loading and storing on our microbit, we start at 0x20000000. So that's an important one. That's the start of our normal RAM, our storage we can access during running a program, and it sticks around until we turn our microbit off. Then there's this other bit of SRAM, the first half a gigabyte, is dedicated to only our program memory. So that memory is usually read-only, or that memory space is marked as read-only. And in this case, it goes up to half a gigabyte. Well, my question is, do we actually have half a gigabyte of space for our program on the microbit? Someone can tell me if you can remember from last lecture. Then we've got these other spaces, another half a gigabyte for peripherals, starting at 0x4 blah. This is how you're going to access the general purpose input-output pins, LEDs, buttons, all kinds of stuff, etc., etc., etc. So we've got this area for peripherals, which is going to be where the memory mapped registers to change and affect peripherals is going to be stored. The private peripheral bus is all this weird stuff that I don't really know what the private peripheral bus. External device, I don't know what that means. External RAM, I don't know what that means. This is actually all a little bit generic because it's just to do with the ISA, the ARM v7 ISA. Someone's just asked me, is the speaker also in the peripheral section? In fact, it is. The speaker is hooked up to one of the GPIO ports, so it's in the peripheral section. Someone's saying that the code memory, well, maybe we can only store like hundreds of kilobytes of code. Absolutely true. So we're never actually going to use 0.5 gigabytes because our microbit only has 512 kilobytes of flash. That's the memory we store our program on when we have our microbit turned off. So it's like hard drive space. So we can't have an 0.5 gigabyte program. It's just too big. In fact, we also only have 128 kilobytes of RAM. So we're not going to be able to use 0.5 gigabytes of SRAM either. That's why I said this is mostly empty space. There's like a tiny sliver down the bottom that we can actually use. Tiny sliver down here. And the peripherals, it's more like there's tiny slivers all throughout it because there's lots of different places where a peripheral has been mapped in. And then I don't think we use any of this stuff. Now, this gives us some information. Let's just try to remember the order of my slides. Oh, we'll get to it later. I want to go into some more specifics about our actual microbit processor, MCU. Now, a memory address is just a number, remember that. So it's not Rigel 7, it's just FA120111 or something. Just a 32-bit number, usually stored in hex. Sometimes the numbers make sense because you might be able to see, if you see a memory address, you can look at the first hexadecimal digit and know kind of what it means. So if the first digit is 2, that's somewhere in RAM. If the first digit is a 2 or a 3. If the first digit is a nothing, a 0, that's in your code memory. If first digit is a 4, it's going to be a peripheral. So these are the different locations in memory you have to worry about. Not all of the memory is the same in our memory space. Some of the things are actually memory, SRAM. Some of the things like the code is stored in flash. Some of the things are actually all the peripherals, which aren't actually memory. They're memory mapped register that is connected to the controller for some peripheral. So you could, if you set bits on that register, they're not actually getting stored anywhere. They're going straight to a peripheral to get it to do something. This goes to say, well, the reason for me saying this is that this tells us something important about the architecture of the microbit CPU. It's called a Loadstore architecture. A Loadstore architecture. So, in fact, on your microbit, everything the CPU does for interacting with the world outside of its own registers and ALU is done through memory addresses. Memory addresses are almost the most important thing to your CPU. And loading and storing is its way of interacting with that information. So you can load and store data to RAM, you can configure peripherals, you can blink an LED, beep the speaker, send a network message, store some data. All of this one is done through load and store operations. So the concept of the load store architecture, this is an important word. I think is there a link somewhere to Wikipedia? Anyway, you can look it up in the further reading links. I think you'll find a link. If there's not one there, I'll put one in later. This is an important word, load store architecture. There are other ways to create a CPU. For instance, just off the top of my head, on our microbit, if you want to blink an LED, you have to store a special value in a special memory address, and then the LED will turn on. Well, that's one way to do it. Another way would be to have a specific instruction, like LED on. Okay, that instruction would be good, but it would only work for this specific computer because the LED would be wired in a specific way. So if we did that and had specific instructions for every single peripheral that we wanted to interact with, our assembly language would be very specific to our computer. And it turns out that modern assembly languages tends to be much more general and then the computer has its own memory map and its own way of interacting with different memory addresses. So the specificness is in the memory map, and then the ISA and the specific instructions that you're allowed to use are very general and refer to lots of different kinds of CPUs. So the Loadstore architecture lets us have an ISA which is kind of simpler than having specific instructions to do specific peripheral writes or activities, but it means that those activities are possible through interactions with memory. Another way of sort of reasoning, a kind of counter example to Loadstore architecture, would be that on the Microbit we don't have any instructions that can write directly to memory except the str instruction. We don't have any instructions that can write to memory except str and all of the strs, the many strs that there are, lots of different strs. But for instance, there's no instruction which can add two numbers and store the result in memory in the same instruction, whereas some ISAs do have that kind of stuff. So that's not a Loadstore instruction, because that means that that adding instruction can interact with memory. The idea of Loadstore architecture is that you only have loading and storing instructions for dealing with memory, and all the other instructions only work in between registers. So we've talked a few times about memory diagrams. I guess the point of this slide is to say that memory is actually a one-dimensional array, right, of bytes. That's supposed to be a B. 0, 1, 2, 3, 4, B, all the way up to B, F, 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 F. And then sometimes we draw it as a kind of square, as a 2D diagram, which means that you're sort of putting arbitrary breaks into the list and moving it down or moving it up. You can go up, you can go down, you can go left, you can go right. It doesn't matter. It's just the layout there is not related to the actual data storage mechanism. That's just a way of representing it to us humans. There's the diagram. Didn't we just have this slide? Oh yeah, so as we said, not all of the memory is data. Some memory locations have different properties. Some can be readable, some can be writable, some can be runnable or executable. You can run them code stored in that location. And some have external peripherals connected to them, which still have RWX or some combination of those properties. So it makes our CPU simpler if we treat everything like memory and just have these properties of readableness, writableness, executableness. So here we go. This is where we get to the actual situation on our Microbit. What is the CPU on the Microbit? Well, it's a MCU, a microcontroller unit, and that's called the NRF52833. So what we need to do to find out what the memory on the NRF52833 looks like is to look in the manual for the NRF52833, which I'm going to do right now. Thankfully, we can look in the manual under Core Components. I can't make that bigger over there. I can look under section 4.2, Memory, and this will tell me all of this important information. The NRF52833 contains 512 kilobytes of flash memory. We already knew that. Where is the memory map? Here it is, 4.2.3, memory map. If in your life you're doing some assembly programming on a new computer, looking for the memory map is usually a thing you would like to do, because it tells you where all the stuff is in memory that you need to interact with. Here we go. So you can see that there's the generic memory map. Code, SRAM, peripheral, RAM, device, device, device. And here's the actual ones that are used on our Microbit. There's a bit of a bump out here for the lowest bits here, because the lowest bytes of RAM, because there's more important stuff down there. So you can see that our lowest address, 0x000000, is actually flash. So when you're running your program, I think it's running straight off flash, and you will see that it's got a very low address. We'll confirm that in a minute. Then at 0x080000, there's some other RAM for storing code. Code RAM, I guess, would be still executable, but stored in RAM. Then there's these two things, FICR and UICR. I don't know what those are. Someone can tell me what they are, and maybe we'll all learn a lesson together. Then at 0x200000, we have our data RAM, as we've been talking about last week. Then important stuff, here's the peripherals. There's some peripherals starting at 0x4 followed by zeros, and some starting at 0x5 followed by zeros. AHB and APB. Both of these things end with B, and they both mean, in both cases, the B stands for bus. A bus is a kind of bundle of connections to other peripheral devices from a computer. A bus. It means a lot of wires all hooked together going in the same direction, and many peripherals can go across those wires and connects to the CPU that way. You might have heard that term, or that letter B is also used in other wires that you know about. USB, Universal Serial Bus. I'm trying to think of another B. Probably not that many these days. We used to have a lot of buses in computers that you deal with back in the 90s, but now USB tends to be the only bus we deal with. APB. So there's actually two slightly different ways of connecting peripherals within a Cortex-M4. I think APB is the advanced peripherals bus, which is like already pretty good for some reason. And then AHB is the advanced high performance bus or something. I think that's what it stands for. So that's an even better bus. I'm not quite sure what the specific differences between those two buses are. I know that they're separate. Some peripherals have to be connected to one, some have to be connected to the other. So you might find some peripherals that start with a 4 in their memory map, and some start with a 5. Now you might wonder what all this means. Where do we find out where different other things are in our memory map? And in fact, in week 4's lab, you're going to start doing some digging inside this manual to work out where stuff is. This manual is almost entirely dedicated to explaining where different things are in the memory map. That's the whole point of the manual. This is going to tell me what AHB was. Oh no, it just says AHB. I'll just go to give you an example. If I flick forward to peripherals, these are our peripheral interfaces. They're in alphabetical order. I want to talk about general purpose input outputs. General purpose input outputs are electrical connections coming out of your CPU, which can be treated either as an output or an input, depending on how they're configured. When the way to configure these things, sends data to them and take data back, is all done through memory addresses. So you can look in this section, 6.8, about how to do the pin configurations, how this all works. There's a lot of stuff here. And now we get to the actual locations in memory. So all of our GPIO addresses are going to start from a base address of 0x5 followed by 7 zeros. So they're on the AHB. Then there's actually two different GPIO ports, port 0 and port 1. And on this particular MCU, we've got 32 pins connected to port 0 and 10 connected to port 1. So there's 42 pins in total. Some of those pins are here on the bottom of your microbit. Oh, where's my spare microbit? I need one to hold up. You know, you got those little gold-colored connections on the bottom of your microbit. Some of these are connected directly to those GPIO pins on your CPU, on the MCU. So you can access those pins through these memory locations. So this is the typical way we describe memory locations. We don't describe them all individually. You typically have a base address and then an offset. So for P0, the base address is 5 followed by 7 zeros. Then the offset for a register for setting the output of those pins is 0x504. So the full address of that out register would be 50000504. And it's handy to have these outsets because you can then start from a different base, 0x50000300, for port 1 and use the same offset. So that's just a little bit easier to handle it when you have to have multiple base addresses to configure different things. And then there's like, look, 1,000,001 different things you can do with every peripheral. Is it incredibly complicated? It absolutely is. Computers are complicated, as it turns out. This is a 600-page manual that explains all of these different peripherals, how they all connect, what all of their base addresses are, what all the offsets are. Look, it's just absolutely chockers full of base addresses and offsets. Then there's diagrams like this, which are showing you what one of these memory mapped registers does. Each bit will do a different thing in that register, and you have to read the diagram to find out. You'll do it in week 4. Gosh, I've still got a few slides left. I better keep going. Code in memory. So you must remember that your code is stored in this same memory map. So as you're going through your program, all of the instructions have been saved into the flash memory on your microbit, and they're getting recalled one by one. So this fetch, decode, execute cycle is fetching from memory based on the address in the program counter register. Let's just have a little go. I've got a program here that I was playing with this week. Someone asked me a good question on Piazza, and I want to look at what the program counter says. Okay, the PC says 0x00000200. When I move down 1, the program counter shifts up by 4. When I move down again, shifts up by another 4. Move down again, shifts up by another 4. So where in memory is my program counter? Whoops, let's go. No, I really wanted my memory map here. It's down here. Got my coffee on my drawing pad. The PC was down here to start with at 0x200, which we know from our Nordic NRF52 manual that this is in flash. So it's reading directly from flash to run our program, which is great to know, isn't it? There we go. What I think I'd like to point out, labels and branching, we'll do that in a minute. So as you're going down, you can think of your program in memory. I'm going to start from the top because sometimes we start from the bottom in those other diagrams, but for programs we tend to read them down the page. So we start from the top and go down. Our program has kind of been written as a sequence of instructions that are read and executed one by one. And you learned this when you started learning to code, wherever you were, whether you were last year in starting computer science at ANU, whether it was in high school, whether it was in primary school, or whether it was in preschool, playing around in Scratch or something. You learned that the computer would run each thing in a sequence going down the page, going down the screen. So that would be 0x200. The next one is 0x204, 0x208, OX2A, something, yeah, I don't know. Anyway, we'll keep going down. Now, if this line of code is being executed, if that one's being run at this moment, this one is where the PC is pointing to. So it's always pointing to the address that it's about to load and execute. In fact, it's pointing to the address that it just loaded because the microbit is loading memory to decode one ahead. Okay. Labels and branching, last thing to talk about today. And something you've probably already played around with in your, 2OC, sorry. Someone's corrected me, I was doing the wrong. Um, 2OC. Someone has mentioned that the lecture is frozen on stream. Unfortunately, nothing I can do about it. I stream it to stream because I know it's available in more countries and I hope it works. Sometimes it doesn't work and I just have to live with it. It's not a very intuitive service and it doesn't give you many options. We're just talking about the streaming for a moment, taking 30 seconds. Like Twitch and YouTube have unbelievably, fantastically optimized streaming platforms. I can start a stream just with one click, an API jumps through my system and starts the stream on multiple platforms at once. I use a platform called Restream to help do that. And it works perfectly on Twitch and YouTube, no problems. Microsoft Stream does not work perfectly. It's incredibly complicated to set up a live event. I have to copy and paste addresses for every single event, start them manually, keep the tab open so that it doesn't crash. It's just a nightmare compared to Twitch and YouTube. I do it because I know that there are people who can access that outside of Australia who can't access Twitch or YouTube, but I wish I didn't have to do it. If you can't watch the lecture now, it will always be on Echo 360 later. Maybe ANU VPN, there's some discussion about this stuff. Someone says, I learned loading from Flash is slower than RAM. At times when the performance really matters, is there any way to use RAM for instructions? It's not going to be any faster in this instance. Yeah, that's a good point, but I think that this is not... that's a very good question. You might have to leave it with me. There's often a way to load a program into RAM and run it, but it's not typically something you would do on an MCU. It's something you do on a big desktop computer. You have your long-term storage, hard drives, SSD, and you typically move all of the code into your DRAM and then access it from there, and then the CPU would be taking chunks out of that DRAM and putting it into cache to try to optimize performance. On the MCU, we typically don't do that, although I'm not really aware about any kind of caches that might be in between these things, but they're much simpler systems, which is why they're good for experiments and learning. But not in this case. You wouldn't typically change things around like that. Yeah, look, yeah, thanks for letting me know about the stream freezing. Nothing I can do. I've used to get very frustrated about it. Now I just try to relax and hope that everything works out. Now, all these 32-bit numbers, very fine for the microbit to remember, but not so good for us. So the labels, this concept of a label, gives us a way to temporarily give a name to a memory address. And you've already seen labels. Main is a label. This is a label. In fact, anything that ends with a colon in your code, main, I've got another one down here, text loop, some crazy function, saved something, these are all labels in your code. Now, wild fact of the day, your CPU doesn't know about labels at all. This exists in assembly, in the assembly language which we write. Then when the assembler sees the label, it just replaces that with the value of the memory address of this line of code. So So these labels only exist for us as handy ways to refer to a memory address, which the assembler later figures out what that memory address is supposed to be, or in fact the linker figures that out. Main is a label. Just a few things about labels. Only certain characters are allowed in label names. Generally you just use letters and numbers, you should be fine. A label is not an instruction, it doesn't get encoded, it's not in memory. It's just it's pointing to an actual instruction. I don't want to have that highlighted. This label is just pointing to the memory address of that instruction. This label is pointing to this memory address. They're the same. It doesn't matter if that instruction is on the same line as the label or the next one, although we typically have labels on their own line. By default, labels aren't visible outside the source file. It only exists in the S file. Then when it's encoded, assembled and linked into the file for the microbit to run, the microbit doesn't know about the labels. The label points to the address of the next instruction, whether it's on the same line or a new line. So labels, it's like putting a sticky note on a bucket. Remember our memory buckets example? This bucket is called main. I'm going to put a little sticky label on it to call it that. This one's called loop. I'll put a sticky label there. This one's called Ben. The reason that this one's called Ben is because the person who originally made this picture was called Ben, Ben Swift, another lecturer at the ANU. So that's his bucket. I should have a Charles bucket here somewhere as well. Charles. Now, this is where things get good. The branch instruction, which you may have already seen this week in your lab, lets us select the next instruction to execute. This is where things start to get exciting in assembly programming. How do we get back to a previous part of our program? We use a branch. The branch instruction changes the value in the program counter to jump back to an earlier instruction. So we can, for instance, just use this B instruction here, B OX 8001C8. That's a memory address, which is the location of the code SRAM, code RAM, not flash. Oh, maybe it's too high for that. Why is there 1, 2, 3, 4, 5, 6, 7. There should be an O. So it is still in the code area, a location in code. So that's handy. This B instruction will let us move around in our program. So if I've got a main label there, and I want to get back to it after doing something, I can type B main. Let's watch the program counter. Someone's probably asked a very good question. I'm just going to read that in a minute. One, two, I'm watching PC here. 208, 20C, 2210, 214. So at the moment, PC is actually pointing to some code that might be here, but we haven't used the branch yet. That branch hasn't been executed. So when I do execute it, boop, we're back up to the original place, OX200. So the program counter is pointing to the area in memory where the program is at this moment, or the next line of code would be. It's not like as you are running your program, the program counter is always going up. It's always increasing, but sometimes it has these big decreases. If you run a B, a branch instruction, it can go all the way back and start again. So as I run my program, I'm stuck in an infinite loop here. My PC is always going up and then back. You can jump forward in your code as well. I could jump to some crazy function down here. How long will this lecture last? I'm almost done. They've got the time. Got to move on. Sorry, I did take a bit of extra time at the start to talk about the assessment. Someone's tutor told them that the indenting doesn't actually matter. Yeah, the assembler doesn't care about your indentation, it's just for your own readability. Typically you would have, this is a very typical code standard, you have your instructions indented and your labels outdented, I guess, just to give you some, so you can easily find the labels in your code. But I tend not to do it when I'm just doing live coding within the lecture. Someone already asked this on Piazza. Why don't we call it jump? Because it feels like you're jumping around your program. There's some other ISAs have the jump instruction, not branch instruction. In ARM, it's just always branch. I guess there's this concept that your program, based on sort of if then else's or loops or something, your program could be going different potential ways, and that there are some potential roads not taken, I suppose. So this idea of branching is sort of, it has this kind of vibe about making decisions to go different ways. There are other possibilities. Where to branch to? So we don't tend to type B0x08 ... We don't put the memory addresses right in the branch. As you've seen already, we tend to use a label in the assembly code to keep track of specific instructions we want to get back to. So you saw me type B main. This is the way we almost always use the branch instruction, like that, with a label, not with a raw memory address. Although you could just type in OX0200, that would be fine. Oops. Here's an example, another example. An infinite loop. We start with R0 as 0. We've got a loop starting, add 1 to 0, add 1 to R0, and then go back to there. So eventually, if we run this program, R0 will loop around back to 0, but it will just keep increasing forever. Remember a few things. Branches and labels are best friends. They're friends forever, BFFs. They go together, and they are the way that you give structure to your programs. Using labels and branches is how you start to create things that look like functions, or look like if-then-else's, or look like loops within your program. Before we stop today, I've got one last little thing to discuss. Sorry, I'm going a bit over time. This idea of conditional branching. So you will have seen in the cheat sheet that, oops, not loads and stores, branches have B, C, which is a condition code, then the label. If C, then PC defined to label. So the branch is defined as just changing the program counter to equal a label, which is a memory address. The condition codes are defined down here, and the conditions are based on the values in the program status register. So conditions based on flags. The flags are how we make decisions about where to go in our program at certain times. So now it should be starting to become clear that the flags are very important for how you're going to have structured programming. This is a huge moment. This is the first time we can make a decision about what to do in our program. Until now, no matter what program you wrote, it would always do the same thing, and it would never deviate from the path that you had set for it. Now we can write programs that actually make their own decisions to go in different ways and exhibit more complicated behaviors. So here's a few of the clearer conditional branch codes. There's the condition EQ, NE, CS, CC, MI, PL, VS, VC. So this one's equals, so it's testing if, it's actually testing if Z equals 1, that flag. That's precisely what it means. But typically what you would do is have two registers and use the compare test, which calculates R0 minus R1, throws away the result, and just sets the flags. So if R0 and R1 are equal, then we know that Z will equal 1. And that means that we can branch if equal. Similarly, if R0 and R1 are not equal, doesn't matter which one's bigger or which one's smaller, then Z will equal 0. And then we can use the BNE branch. BCS stands for carry set and carry clear. I think that's wrong. That should be carry C equals 1, C equals 0. Oops. That's been there for about 5 years in that slide. BMI means that the result is negative, so minus or negative, only if the branches if the negative flag is 1. B plus or B positive is branching if the negative flag is 0. BVS is branching if the overflow flag is set, and BVC is branching if the overflow flag is not set. So you can see that if we were doing some kind of arithmetic operation, we might be able to use this conditional branching to check if the outcome of our operation had set the overflow flag, for instance, and that would suggest that we have to do some other operation because our answer is wrong. We can also use it to get out of a loop. So if I go back to the little loop, I guess just write another program up here, mov R0, 0, loop. And I'm going to add R0, 1. Okay, this was my infinite loop. R0 is just going to keep adding up and adding up and adding up together. There's no other loops. I've got text loop. You can't have multiple labels called the same thing. So if you've got a label called loop, just be careful with that because you might have more than one loop in your program. So the assembler will tell you if you're doing it wrong, but just to be aware of that. If I want to get out of my loop, I could have another label down here called exit loop. So what I might want to do is compare R0 with 4, and if they are equal, go to exit loop. I wonder if that's going to work. I sometimes forget which instructions you're allowed to use immediates with. Yeah, that works. R0 is 0, okay. R0 is 1, add 1 to R0, compare with 4. We're not doing anything, but the 0 flag is clear, so we're not going to be taking that branch. Back to loop, add 1, try the compare again. Remember the compare goes R0 minus 4 in this case, and throws away the result, just sets the flags. R0 is 3, try again, hasn't worked. Okay, now R0 is 4, compare R0 with 4, our 0 flag is 1, BQ exit loop should go to the exit loop, and we're out of the loop. So finally we can escape infinite loops with conditional branching. There are some other conditional branches, unsigned, lower or the same, greater than or equal, less than, greater than. These are for signed. The GE, LT, and GT and LE are for signed 2's complement interpretations. We might go through those next week just to make sure we understand how they work, because you can see they're a little bit n equals v. Negative is the same as overflow. It's a little bit tricky to work out why that should guarantee that one of our numbers was greater than the other or equal. But we'll look at that another time. The last thing in this lecture, I promise you. How do the labels get turned into memory addresses? Well, it's a program called the linker which does this. When you build one of the programs for your Microbit, as we just did then, you might see in the terminal this information comes up running these two programs. GCC is the compiler, which is assembling our code for us, and then LD is the linker. And the linker's job is to put everything in the right place in memory. And it's all defined, we'll look at this a little bit later in the course, but it's defined in this thing called an LD file, a linker file, which knows where all of the memory locations are for the microbit. It's all set up there. There's 512K of flash starting at that address. There's 124K of memory, of RAM starting at that address. And then there's this little extra bit of code RAM, 4K, starting at this address. So the linker knows this information, and the linker replaces out all of these labels for the correct memory locations for us. And your CPU never knows about these labels. It's just the linker that knows about them and replaces them all with memory addresses for us. Now I'm going to skip that last slide. We'll talk about that stuff another day. It's just some sort of important roles of the linker to make sure that read-only memory is read-only, that we can't execute, we can't run memory which is not supposed to be run. All of these kind of security, don't let my computer crash stuff is controlled by the linker in this context. And that's all I got for you today. Feel free to jump out of the lecture now, but if you've got a burning question, I'll do my best to answer it for another 5 minutes. Sorry I went a little bit over time, but I do tend to do that on a Thursday morning. I realize now that I think I'm going to revise this resources page today to give it a bit more structure. It's sort of a big list of stuff. And I want to structure it because there's in fact 3 important huge manuals. Well, they're all huge, but they're different and important. The first one we looked at was the Architecture Reference Manual. And then today we also looked at the NRF52 manual, that's the MCU. But there's also a technical reference for the Cortex-M4, which is the CPU inside the NRF52. And we also need that manual to understand the particular features of the CPU. This manual is fun because it gives you this nice, first of all, it's online, which is a little bit easier to understand. It gives you this nice summary of all the instructions that are possible on the Cortex-M4. So your microbit can run any of these instructions. So if you just want to have a little look at the instructions in a slightly more concise format, this is the place to see it. And also in this column down here, it tells you how many CPU cycles each instruction will take. There are some that take a long time. Division can sometimes take a long time. It does other stuff to manage to do a division. Cool. Yeah, okay, well I haven't seen any other questions popping in. So I think that for today, I will say goodbye. Have a great weekend. It's a long weekend here in Canberra, but do look at the assessments page. I'll be posting on Piazza later today to keep you up to date with all of the latest developments there. Thanks folks, and I'll see you next week on Tuesday morning, because Monday is a public holiday. I'll be streaming on Tuesday morning instead. See you later.